Hi everyone, Dankman here. Today's topic continues solving systems of equations with this new technique called elimination. Yesterday I introduced elimination and talked to you about what it would mean to add two equations together. Today we're going to introduce this new wrinkle that will call on us to do something special, namely subtract two equations. The review section is going to be really short. I'm just going to do another example problem that matches what I introduced yesterday. So yesterday was, hey, here's a system of equations, solve it. Here's an example that matches what we did yesterday. 6x plus 10y equals negative 10, negative 9x minus 10y is equal to positive 10. Solve this system. Okay? We could try to graph it. Maybe the graph would look something like this. I don't really know for sure. If I had to guess, it'd look maybe something like that. And try and find the xy pair represented by the point that's on both lines and plug that in and check it. But graphing these kinds of equations is challenging, maybe a little messy. We could try to do substitution here, but it's not super convenient to use substitution here. We would have to solve one of these equations for one of the variables, and that would end up with a bunch of fractions. So we introduced this new method called elimination. And in the beginning, the elimination method is a little bit weird, because here's what we did. We took one equation and we said, look, we're going to try and solve this equation for one of the values, either for the x or for the y. But to solve an equation like that, we need to eliminate one variable. We need to turn it into a single variable equation. That's what substitution did for us before, but that's too messy for us to want to do that now. So I proposed this idea that I, of course, did not make up myself. And it was the following idea. I want to basically add the same thing to both sides of this equation. Add the same thing to the left side and to the right side, but do it in a sort of clever, interesting way that allows me to convert this equation into a one-variable equation. All right? And so up top, it just so happens that the left hand of this equation, negative 9x minus 10y, and the right hand of this equation, positive 10, that if I add the left-hand side of this equation and the right-hand side of this equation to the top equation, something cool will happen. So even though I'm adding something that looks different on left and right, since the left side and the right side of this equation are equal, even though it looks like I'm doing a different operation to the left than I am to the right, underneath it all, I am doing the same operation to both sides, so I will get out an equivalent equation. I won't change the solution. Okay? And that process looked like this. I take everything in the top, 6x plus 10y, and add everything in the bottom, plus negative 9x plus negative 10y equals negative 10 plus 10. Okay? Rearranging to move towards simplifying, I get 6x plus negative 9x plus 10y plus negative 10y is equal to 0. Combining like terms to simplify and see a little more clearly, 6x plus negative 9x is negative 3x. Positive 10y plus negative 10y is 0. So I get negative 3x equals 0, and indeed, I have turned the original equation into a one-variable equation, and that means now I can solve this equation, x is equal to 0. And of course, I am looking for the xy pair that solves both equations at the same time, so I only have one part of my solution, the x part of my solution. Now I wonder to myself, okay, look, if I have, for instance, 6x plus 10y is equal to negative 10, that's my top equation, and I know that the solution I'm looking for has x equal to 0, I'll substitute in 0 for x, and that way I can now find, okay, 6 times 0 is 0, plus 10y equals negative 10. What I now know is that if x is worth 0, I substitute it in, and I get a single variable equation now, and I can solve that single variable equation for y to get y is equal to negative 1. Okay? And so I've found my solution to this system, the xy pair that I wanted, x equals 0, y equals -1. And what have I accomplished? It's always good to go back and check a little bit and make sure you understand what it is that you've just accomplished. So I'll do my check. I had two equations, 6x plus 10y is equal to -10. -9x minus 10y is equal to +10. And if I take my left-hand equation here, I'm going to ask myself, does this xy pair actually solve it? Well, 6 times 0 plus 10 times -1 equals -10. So I substitute in 0 for x, -1 for y, and I see if the equation is satisfied. 0 plus -10 gives me -10 on the left, -10 on the right. So I did find a solution to that equation. Let's substitute in 0 for x and -1 for y. I get 0 minus -10 is equal to 10. And this 0 minus -10 becomes a +10. So both equations are satisfied by this solution. That was the introduction to the elimination method. It's a way of taking two variable equations and eliminating one variable, finding what the other variable's solution value must be, and then plugging that back in to get both. All right? But there is a different kind of issue that can come up with these sorts of problems, and that's what I'm going to show you with the next example. Before I start that next example, notice at the very beginning we had two different equations. Okay? I combined those two equations by adding the purple equation to the top equation, and when that happened, I got lucky because +10y and -10y combined with each other to eliminate all the y values from this equation, leaving me with a single variable equation that I could solve. But I won't always be so lucky. Okay? Let's look at a second example to understand that. So the instructions would be the same. Solve the system. And this time my system might look like this. 5x plus 2y is equal to 28, and 5x plus 6y is equal to 24. Now I'm going to lead you astray momentarily. Okay, I'm thinking to myself, okay, Dankman's assigning me an elimination problem, cool. I'll just do exactly what I'm told, which is just line them up, draw the golden road. I can see here that the bottom equation has 5x plus 6y on the left and 24 on the right. I'll just write those things down, and I'll go ahead and, well, I know how to add equations, so sorry kids, I'm going to lead you astray here for a moment. I'll go ahead and start adding equations. So I'll do 5x plus 2y, and then I'll add 5x plus 6y, and then I'll do 28 plus 24, and then when I go combining that, I'll combine 5x and another 5x for 10x, and I'll combine 2y and another 6y for 8y, and 28 plus 24 gives me what? 52? But then nothing good has happened here. I haven't gotten any closer to where I wanted to be because I haven't eliminated a variable. I haven't created a single variable equation. So this whole thing wasn't very helpful to me. Okay? And so there's a little reality here. Little reality check, which is that you can't just go adding equations blindly for elimination method to always work. What some people call linear combination, you're sometimes going to have to get clever about how you combine the equations. So, in this case, we added the same value to the left side and to the right side, but it didn't end up helping us eliminate a variable. However, if we had been super careful, we might have noticed that if we had, instead of adding, if we had subtracted, we could have gotten 5x minus 5x, and that would have eliminated the x variable for us, leaving behind only a y variable. This is a lot to take in, but it's going to be a multi-step process, so calm down. So here's what I'm going to do. I'm going to do the same thing. I'm going to take my top equation, 5x plus 2y equals 28. I'm going to draw my golden road and prepare to solve this equation. And I do want to make sure that I put the same thing on the left side and on the right side. And in this case, the left side is 5x plus 6y, and the right side is 24. But if I add them, they don't help me at all. So this time I'm going to subtract. All right? And watch what happens. You have to be really careful with subtraction because I have 5x plus 2y for the top, but now I'm going to subtract each piece in the purple. So I subtract 5x and I subtract 6y. And on the right-hand side, I have 28 from the top, but I subtract the bottom 24. Rearranging now, I get 5x minus 5x plus 2y minus 6y is equal to 4. And combining like terms, the 5x positive and 5x negative cancel each other out, or they're a zero pair, so they disappear or annihilate each other, and then I get 2y minus 6y for negative 4y equals positive 4. So I have eliminated the x variable from this equation, giving me a one-variable equation that I can now solve. Now that I've solved for y, I take either of my original equations, like 5x plus 2y equals 28. I substitute in the y solution that I found. And in this way, I can solve for x. And so, I believe I have found my solution. X equals 6. Y equals negative 1. It's always good to check in and see what you've accomplished. So we'll take 5x plus 2y equals 28. And 5x plus 6y is equal to 24. And I'm going to plug in 6 for x and negative 1 for y, and see if I get a solution, or if my pen works. Yeah, that equation is satisfied. I'll try the other one. I'll replace x with 6, and replace y with negative 1, and I get 30 minus 6 equals 24. So both equations are satisfied. The big takeaway here, you can combine two linear equations in order to solve a system of linear equations. For instance, in this case, I added my two equations together, and because I had a positive 10y in the top equation and a negative 10y in the bottom equation, the y variable got eliminated, and that left me with a single variable equation that I could solve for x here, and from there I knew how to solve the system. But in this case, when I went to go adding the top and bottom equations together, the magic didn't happen for me. One of the variables was not eliminated. I just created a brand new linear equation that didn't get me any closer to solving. So I had to be super clever and look out and see, okay, wait a second, is there something else I can do, some other operation I can do to both sides? So I recognized that if instead of adding the top and bottom equations, if I subtracted the bottom equation from the top equation, then I would get 5x minus 5x, eliminating the x variable, creating a one-variable equation that I could solve, etc.